This
Morning,
conference will now be recorded.
Okay. We are happy to have Encik Anwar Osman from Rod Schwartz. He will share the topic of resolving the interference of 5G base stations towards the satellite service incumbent in C-band. Okay, with that, I pass to Encik Anwar.
Terima kasih. Thank you to Ms. Shanfa for the introduction. Right. First of all, I would like to thank all of you for attending this talk, and I hope that this presentation benefits to the participants. So as you can see, the title of the presentation is resolving the interference of 5G base stations towards the satellite service incumbent in C-band. So this title or this topic is actually being discussed rigorously in the 5G task force that we had last year. And without further ado, let me start with the presentation. So this is a little bit of myself. My name is Anwar. I'm a regional application engineer from Rod Schwartz. Our office is in Shah Alam, and Rod Schwartz is a German company specializing in test and measurement. So 16 years of experience working in wireless communication and mobile network testing. So my previous life actually was in Penang, so I worked in Intel, Motorola, Abago Technologies, SXCs, and Agilent. So mostly on the R&D and application engineering, doing the same thing, which is communication and LTE, 3G technology, design and management. I'm also a senior IEEE member. IEEE is an international organization and association for electrical engineers. I was part of the Malaysia 5G task force team, and I was appointed as the chairman of the 5G ecosystem and timeline sub-working group under the spectrum working group. So this working group is the one discussing and trying to find a resolution towards this issue of coexisting the 5G technology in the C-band as well together with the satellite services. Currently, I'm the vice chairman of MTFSB, IMT, and Future Network Working Group. So under this working group, we are responsible in producing the technical codes for 5G system, as well as the EMF measurement and deliberation for base stations in Malaysia. And I have I've graduated from USM with a master's degree. So let's start with the presentation. First of all, just a little bit of what the agenda of the talk today. The first thing I want to discuss is why is this C-band in 5G? It is part of the 3.5 gigahertz band is important for the 5G deployment, for 5G early deployment, and also why is C-band important for satellite service as well. So we need to know why these two technology have to use this C-band, right? And then we will look into the possible interference from the 5G base station towards the current satellite service providers in Malaysia. And then we will discuss the mitigation technique, right, that we can deploy to reduce or eliminate this interference. And we will also briefly look into the field test plan as recommended by the 5G task force. And this plan is actually published together with the task force report in Appendix A. So the plan shows or explain the steps and the method that need to be done to obtain the coexisting scenario. Coexistence means that both the 5G and satellite service can coexist together in the C-band, right? And lastly, just a little bit of case study in Hong Kong, how they do the test and what is the conclusion for the test. As you know, in Hong Kong, they have started 5G starting 1st of April. Right? So the study that they have made in Hong Kong actually helps to enable the deployment of the technology, especially in the 3.5 gigahertz or the C-band. Right. So next, let's look here. Like here. Okay, 5G is here, right? In many countries, we have more than 50 commercial 5G networks already, and the countries that already deployed the 5G technology has increased. So this is actually a bit updated. 37 countries. I think it's now close to 36 countries at the moment. So in 5G, right, there are three bands that we can use for deployment. The first is called low band or sub 1 gigahertz. So for this band, it's actually more for coverage. So in the rural area or non-urban areas, so we want to utilize this band so that we can have few base stations that can do a very large coverage for the service. However, for this low band, because of the limited bandwidth, then the capacity of the service will be low, right? So that's the drawbacks of using this band. And the second band is called mid band or the sub 6 gigahertz. This is where the C band is located, right? The 3.5 gigahertz band. So over here, we have a good balance of coverage and also capacity because it is still in a relatively low frequency that we can for the base station to do a large area coverage, and we can actually get 100 megahertz of contiguous bandwidth for each operator so that we can have good capacity. And the third band is the high band or the above 6 gigahertz. This is in the 3GPP is called a millimeter wave band, right? This is very high at 28 gigahertz. So for this high frequency range, we will have problem with coverage because the signal will not go far from the base station, but we have good capacity because the bandwidth, the potential bandwidth is huge here. So the service will be very fast and very low latency. So in terms of the mid band, mostly we talk about C-band spectrum. Currently, it has been licensed to 64 operators for 5G. Now, this is very important because if you look at the next slide here, right, within the sub 6 gigahertz range, right, 3.5 gigahertz has the largest number of trials. So meaning here, the network providers like Ericsson, Nokia, ZTE, and Huawei, right, they will have the base station ready at this band. So the ecosystem is there, and that is why it's very important for the 5G deployment. One of the 3GPP designated band for 5G is called N78. So this band is actually covers from 3.3 to 3.8, right? 3.8 gigahertz. So this is unfortunately part of the C-band, right? So this is why this C-band is important for 5G deployment. Right? The 3.5 gigahertz band can provide both, as mentioned, can provide both coverage due its propagation characteristic, and it also has the capacity, right, so that we can have the required or expected service performance from 5G. The first wave of 5G deployment will be focusing on delivering the EMBB or the Enhanced Mobile Broadband Service. So what this means is that the service need to deliver a peak download of 20 gigabit per second, and as well as other performance criteria, right? So we need about 80 to 100 megas of spectrum bandwidth, and the 3.5 gigahertz band is able to provide this bandwidth for each operator, right? And also for the worldwide 5G ecosystem, right? The base station, the phone, the 3.5 gigahertz band is the most supported in terms of availability, right? So if we want to deploy 5G quickly, right, we want to get the equipment that is already available, the phones, the PlayStation. So if the ecosystem is already there, then it will be easy for the country to deploy. So in terms of the ecosystem, in terms of the coverage requirement and also the capacity, right? So these three factors are the one that makes the C-band important for 5G deployment. However, right, C-band is already occupied, right? So let's look at who are the current operators of C-band. So the current use of C-band varies across the regions and countries. Some countries have already made C-band vacant, right, to anticipate for 5G use. However, many countries, especially in Southeast Asia, Malaysia, Thailand, Indonesia, Brunei, Vietnam, right, they are still using C-band for other service, mainly the fixed satellite service, or we call it FSS. So the FSS in application in C-band include a large satellite earth station, which serve a gateway that carry trunk or network traffic towards the space station, the satellite in space. Secondly, it can also be used as a telemetry, tracking, and command station, or TTNC, which provide the vital telecommunication link between satellite and the ground station. In Malaysia, we have a few of these stations. One in Cyberjaya. If you can see at the backside office area, then near MCMC, there is a big satellite dish, right? That's for the TTNC, which operates also at C-band. Next, the most common use of FSS, especially in Malaysia, is the VSAT service, which are the two-way satellite system primarily used by business as well as government application. Now, an example of VSAT, if you realize at the petrol station, at the petrol station in Malaysia, there is a satellite dish. So that's for VSAT services. So the payment for when the petrol lorry, right, or the petrol truck, when they arrive in the petrol station, right, so the petrol station have to make the payment via the satellite this VSAT service, basically. So if there is an issue with the payment, then the petrol truck will just leave, and there's no they will not fill in the petrol station. So that's one example of this VSAT services. So you can see that it's critical and it involves the public. And lastly, another FSS application in Hong Kong and in Indonesia is the satellite master antenna television, or SMATV. And this system actually use a multiple broadcast signal from satellite and create a single integrated cable signal to distribute via a cable network. For example, in the flat or high rise residential apartments, right? They have a satellite receiver at the top, at the roof of the building, where it receives the signal from the satellite, and then it distribute the signal to all the houses, all the units in the flat or in the apartment. So these are the current usage of C-band currently, right? So let's look at the regional incumbent of C-band. You can see that countries like Thailand, Malaysia, Singapore, Indonesia, Brunei, right? From 3.4 gigahertz to 4.2 gigahertz, these are currently occupied by the satellite service. So what we want when we want to deploy for 5G, right? We want to make use of this frequency range, right? From 3.4, 3.5, or to 3.6, or even further. So we want to take some of this band here, right, to be used for 5G, and the remain we still use it for the satellite service. So that is the plan, right? And in the 5G task force, the report recommends that for the 5G operator to be allocated from 3.4 gigahertz up to 3.8 gigahertz for 5G use, and the rest remains for the satellite use. That is what being recommended by the 5G task force report. Now, let's look at the importance of C-band for satellite service, right, especially in Asia Pacific. So if you look at the report from Global Satellite Coalition in 2019, Asia Pacific is being served by more than 16 C-band satellite systems and more than 80 geosynchronous C-band satellites. There are close to 4,000 TV channels distributed in the C-band with more than $56 billion of pay TV revenue alone. This is just for pay TV, not including the petrol station revenue and all that. Right? So it's huge. Right? So C-band is still very much important for the satellite service in Asia Pacific, and practically there is no substitute for C-band for the satellite service. Right? Another thing that we need to know, why Southeast Asia region is using C-band for the satellite service as compared to the other countries. This is due to the rain attenuation. In countries like Japan, South Korea, Australia, the raindrop is small. Right? So the satellite signal at higher frequency may not be attenuated. Right? So this is called the rain fade. So they can move the satellite service for VSAT to other frequency, and they can vacate the 3.5 gigahertz of C-band for 5G. And then we have countries like India and Pakistan, or the South Asia countries, which have still have a bit of issue with the rain fade, but not so much. They don't also have a large users for C-band and the satellite service. But the highest risk will be our region here, right? Starting from Taiwan, Hong Kong, the Southeast Asia, up to the Pacific countries. This is where we are located in the tropical region, right, near the equator. So when it's raining, especially in you can see in Malaysia, right, it's very heavy, right? And the raindrop, the droplet of the rain is big enough that when the satellite signal at higher frequency go through the rain, it will be distorted. Right? It will be there will be a what do you call that, disruption in service. Right? So if you realize that when you are watching Astro, right, when during the heavy rain, there is a problem, right? So this is due to the rain fade, and Astro is at the 12 gigahertz range. So you can see that at high frequency, the rain fade start to have an effect for the satellite service. But in C-band, it is actually immune. If the service is using the C-band band, the frequency range at C-band, it is immune from the rain fade. So even in heavy rain season, we can still get good service. So let's now look at the challenge in deploying 5G at C-band, right? So once the C-band had been reallocated to accommodate both 5G and the satellite service, there will be potential interference coming from 5G towards the satellite receivers. So in C-band, right, the satellite signal is downlink, right? You can see that the signal is from the satellite to the Earth station. So when the signal reaches the receiver, it is already low level because of the attenuation due to the long propagation path that the signal has to go. And if you have a nearby 5G base station, which also transmit the 5G signal at C-band, the 5G base station will cause interference to the satellite receiver. So this is the potential interference that we can expect when we will deploy 5G towards the satellite service. Okay. So basically, it's a bit of technical here, right? There are two main potential interference from 5G to the satellite service in C-band. The first one is due to the receiver blocking, right? Caused by saturation from high 5G signal, right? So basically, right, we have a 5G signal at 3.5 gigahertz, and the satellite service starts from 3.7 gigahertz. When you have a high power 5G signal from the 5G base station, then you start to have a distortion at the satellite service. This is because that although we have segregated the frequency, but the satellite receiver still listen across this band. So it distort the performance of this satellite receivers, and this is called saturation. So this is one of the potential interference that we can have when we deploy 5G near the satellite receivers. The other potential is that, let's say we have a signal that is side by side, right, in the spectrum. So you have the 5G base station here at 3.6, and you have the satellite service at 3.7. Some of the signal here from 5G base station might spill, because it will not be perfect, and if there is not enough filter from the 5G side, then it might fill here. So this is called out of band emission from the adjacent 5G signal. So this spurious emission or out of band emission caused by the adjacent service of 5G towards the satellite service. So it's caused the signal to noise ratio of the satellite receiver to be lower, and you cannot get the signal properly. So there are a few mitigation that we can deploy to prevent this interference. The first one would be to put a guard band. Means that, for example, scenario, we segregate the C-band from 3.4 to 3.6 as 5G, and then we put a 50 megahertz guard band or 100 megahertz guard band from 3.6 to 3.7. Then only we start the satellite service. So this is a guard band that we also propose in the 5G task force. And then another proposal is also to put a bandpass filter at the satellite receiver. Remember, I mentioned that even though we have segregated the frequency, but the satellite receiver still listen the signal that is coming from the 5G. So we can put the bandpass filter at the satellite receiver to block the noise from the 5G base station. So these two are the main mitigation technique that we can deploy, and this is also what has been recommended by the 5G task force. Right? Of course, there's other mitigation technique that we can use, but for mass 5G deployment, it is recommended that this to use these two mitigation hand in hand, the guard band and also the bandpass. So let's talk about the guard band first, right? When we want to deploy 5G in C-band, right, so normally the countries will do a frequency segregation. Right? So the frequency segregation means that the regulator plan to give. Okay, let's look at this. This is the existing allocation of C-band, 3.4 to 4.2 gigahertz. So we want to segregate where some of this C-band frequency range will be allocated to 5G. Right? This is can be anything like from 3.4 to 3.5 or 3.6, whichever that's determined by the country. And then we want to put a guard band, right, to protect the satellite receivers. Okay. So the size of the guard band, either 50 megahertz or 100 megahertz, is actually based on the performance of the bandpass filter, as mentioned as previously for the second mitigation. Right. So the second mitigation that I explained is to at the bandpass filter. So the bandpass filter can be deployed together with the guard band as a mitigation technique that can enable coexistence between the 5G and the satellite services. So the bandpass filter characteristic will determine the size of the guard band required for the coexistence. So of course, to get a good bandpass filter, we need to do some analysis, measurement, to make sure that the important parameters that we expect from the bandpass filter is met. So the coexistence study, as recommended the 5G task force, to enable the two technology to live harmoniously between each other, right, in the C-band. First, to understand what is the test plan required. Right, this is called test matrix stage. Over here, we discuss the test cases, the test parameters, where to do the test, right? And then the next stage will be the theoretical study. This is where we do the calculation and also to determine the specification of the bandpass filter and the guard band, and also to do a baseline measurement. Then we do a lab test, right? For lab test, we do the mitigation study where we have the guard band and the bandpass filter together, and we do a test to filter or to reduce the number of test cases that we want to go for the field test. We only want to do the test cases that are important and relevant. So this is where we do the filtering of these test metrics in the lab test. And then we have to do a field test, right, to simulate the real life scenario, right, real condition scenario. So this is where we do the test based on the test cases that is already filtered out by the lab test, and we will identify the limit of the distance between the 5G base station and the satellite service receivers, and also to do some evaluation, and importantly to get the coexistence scenario. And finally, of course, to come up with a report to present the finding and the conclusion, as well as to give recommendation that will be useful to the operators when they want to deploy and build their 5G base station. So this is a quick example on the first stage, which is a theoretical study. For some perspective here, right? Without the mitigation, right? Without the mitigation, the minimum distance that we need to have to protect the satellite service from a base station, 5G base station, is about 13 kilometers. So for each petrol station that you see, you cannot have 5G. For this is the scenario, then we cannot have 5G, right? But if we put in the filter, right? If we put in the filter, you can see that from this 13 kilometer can be reduced to 24 meter. Right? So we can look at the conclusion here, right? So in a rural scenario or line of sight scenario, we can reduce the isolation distance or the safe zone from 13 kilometers to about 135 meter or 270 meter. And in the city or in an urban scenario, we can actually have only 70 meter. So I think this is achievable. So that is the reason why we want to do the theoretical study, to know the limit when we want to do the lab test or the field test. And after we have some idea of the coexistence scenario in the theoretical study, then we do a lab simulation. So basically, we want to simulate a condition of the satellite service while being near to the 5G base station. So this is the lab setup where we have the signal generator that produce the satellite service, and also another signal generator to produce the 5G signal. And we go to a combiner, and remember we have the bandpass filter and the guard band set up in respectively in the signal generator here. Right? And then we measure the performance. Meter performance, we want to see whether 100 megahertz or 50 megahertz can enable coexistence, okay, or whether we can see there is interference or not. Right. So there is some result that we have made in Rode and Schwartz, and I can go straight to the conclusion that the coexistence scenario can be simulated in the lab for the guard band of 50 megahertz. So this is based on our lab test. So we conclude that the mitigation of adding a bandpass filter and a guard band of 50 megahertz can reduce or eliminate the interference from the 5G towards the satellite signal. And then once we have done the theoretical study and the lab test, we have to do the field test. Right? Initially, I think we planned from the 5G task force to do it in Langkawi, right? But there will be some changes to that. So the scenario, we have to do rural, suburban, and urban scenario to measure the line of sight and non-line of sight. And these are the variables that we need to analyze for the field test. One is to do a separation distance, the direction between the satellite service antenna and the 5G antenna, and also the elevation. The elevation here means because some of the satellite receiver is pointing directly to the sky or close to 90 degrees, but some are actually lower in terms of elevation. Let's say the satellite service is getting a satellite signal which is in geosynchronous in Africa, right? And then the elevation will be lower. So the lower the elevation, the higher the risk of interference. So for the field test scenario, right, for varying the separation distance, so basically, as per recommended by the 5G task force, we have a base station here transmitting at 3.5 to 3.6 gigahertz, and we have a satellite service from 3.7 to 4.2. Sorry, right. So we will vary the distance, right, and see whether there is interference or not at the satellite decoder, right? Satellite decoder here, right? So you have 5G coming in here, and then the satellite signal coming being received by the decoder. We want to see whether there is an interference at distance 1, distance 2, distance 3, and so on. Right? We want to find out what is the minimum distance, right, for the satellite decoder before it start to experience degradation or interference. And now we also have to do the variation of direction, meaning either line of sight between the 5G antenna sector and the satellite antenna. And this is top view, this is top view, right? And also the varying antenna elevation means that we need to try and see the service that coming from high elevation satellite or lower elevation satellite. So the higher elevation of the satellite antenna, then there will be less interference. But the lower elevation means that the satellite here is facing closer directly to the 5G base station. So these are the three parameters that have been recommended by the 5G task force to be tested in the field test to find what is the coexistence or best coexistence scenario for the two services to exist together. Now let's look at the case study in Hong Kong, right? So in 2017, right, Hong Kong planned to reallocate 200 megahertz for 5G from 3.4 to 3.6, and then they plan to at the time they don't know what is the guard band yet. So by doing the study, they found out that the safe guard band would be 100 megahertz, right? And the rest of the C-band, which is from 3.7 gigahertz to 4.2 gigahertz, remain as the satellite service, right? And this is guard band of 100 megahertz. So this was the plan by Hong Kong, right? And they have the same problem as us, but in their case, it's more on the SMA TV. So you can see here, my colleague in Hong Kong is doing the test for them, right, for the field test. So this is the satellite dish, right, and this is the feed horn, and we actually put in the bandpass filter in between the feed horn and the LMB of the satellite dish, right, for the to reduce the interference. Okay, so that was being done in Hong Kong. So what was the conclusion from the Hong Kong scenario? So because in Hong Kong, right, like I mentioned, they have a scenario where the satellite antenna, right, the satellite antenna can be higher than the 5G antenna. In Malaysia, mostly the satellite antenna is at the ground level, right, at of 5 meters above the ground. For example, in the petrol station. But in Hong Kong, there can be a scenario where it is the same height or higher, right? So the conclusion of what they have learned from Hong Kong, based on the study, is that if we apply 100 megahertz guard band and we deploy the filter at the satellite receiver, we can achieve coexistence if the satellite antenna is same height as the 5G antenna, or if the satellite antenna is higher than the 5G antenna. Right? So we can achieve coexistence. It means that you can put it side by side, and it will not face any interference. However, in the third scenario, right, where we have the 5G antenna lower than the the satellite service antenna lower than the 5G base station, and this is the scenario in our country. The majority scenario in Malaysia will be here, right? So unfortunately for this scenario, right, even though that you have put in the guard band of 100 megahertz plus the bandpass filter at the satellite system, we will still need a safe zone of 65 meters. So this is what we have concluded in Hong Kong. And this value or this conclusion is helpful for the 5G operator when they want to deploy the 5G base station, because they will know that for every site that have a satellite service, they need to be 65 meters away. So that is the guideline. So that is what we want to achieve in Malaysia as well. We want to find the this is called the coexistence scenario, the optimum coexistence scenario. What is the guard band? We cannot go for very high guard band. Let's say 100 megas is a bit too high, because it will be a waste of spectrum, right? And spectrum is a resource. But we cannot deploy a too low guard band, for example, 20 megahertz or 30 megahertz, because it may not be feasible. Technically, it cannot achieve the intention of eliminating the interference. So we want to find the sweet spot. What is the optimum guard band, right? So that is one parameter that we want to get for this coexistence scenario. The second, which bandpass filter that is best to be used. We have a few bandpass filter, right, and we need to test, and we need to make sure that it is not too costly, right, and it is easily available and can be installed easily in the satellite system receiver, and still can help to reduce the interference and work hand in hand with the guard band. So these are the second parameter that we want to get. And the third parameter that we want to find out from the study is that what is the minimum distance even after we put in the mitigation, right? When we have the guard band, we have the bandpass filter, but how far we need to separate these two services. For each petrol station, how long the distance will be before we have a 5G service. Means that, unfortunately, if you look at this case, the residential area that is close to, or office area that is close to a petrol station might not get the 5G service at 3.5 gigahertz. They can still get the 5G service from different band, let's say 28 gigahertz or 700 megahertz or 2.6 gigahertz, but not at 3.5 gigahertz. But this is what we want to find. We want to know the limitation. We want to know the coexistence scenario. So that will be the process and the method to resolve this hot issue currently that we are facing to enable us to deploy 5G in Malaysia. I think that would be the end of my slide. I would like to pass back to the organizer for any question and answer.
Okay, thank you, Encik Anwar. Now we open to Q&A. Anyone has any question to Encik Anwar? Ada? Or you can write from here. We have a chat platform here. Okay, looks like there's no question. Okay, before we end, I would like to say that I will send the Google evaluation form to the participants later. I really appreciate that you can send back to me. And with that, thank you, Encik Anwar. We will meet Encik Anwar again on the 28th July.
Yes,
Yeah, Encik Anwar?
inshallah. Inshallah.
Another topic. Okay, thank you all. Thank you, Encik Anwar.
Thank you, Puan Sharifah, and also thank you to MCMC Knowledge Sharing Center for inviting me for this talk.
Okay, see you again. Thank you.
Thank
Assalamualaikum.
you. Salam. Bye.
Bye. Ganis.